All right there, ladies and gentlemen, let's talk a little bit about triangle congruency shortcuts. Okay, so we definitely built this case in class, and you've seen me try to build a case, or at least review the case, that all this really boils down to is if I have a triangle, and all I know is the side lengths, for example, and it's a triangle that someone else has, and again, they only know the side lengths of that triangle, and those side lengths all match, is that enough to guarantee that both triangles that were made separately are actually going to be the same triangles? In other words, we really have to know the angles, we know the sides. And of course, there are combinations besides just the sides I ask you to play with, but that's what we need to talk about. So there's lots of ways we can convince you of which of the shortcuts actually are sufficient to assume the rest of the information and which are not. And this template, or this little program I'm going to show you, is going to try to convince you using a very nice visual argument. So down here I can set a triangle condition. So let's just set side, side, side. So what right now, I cannot move these vertices at all. I'm sorry, the side lengths. I can just move the vertices, but now the kind of assumption here is I have to make a triangle out of this. It goes back to this idea of like initial conditions. Like if I don't even make a triangle, I can't discuss whether or not it's enough to assume pieces of the triangle. So I have to form a triangle out of this. And when I do, the triangle will simultaneously color in, and you see the vertices pop up. So out of those three side lengths, and down here they're listed, I have 19, 14, and 16. I can make this blue triangle, which I'm just going to simply drag over to the side. So what I'm going to try to do now is intentionally break this definition. In fact, I'm going to try to make a different triangle out of the sides. So I'll do like, maybe a little flippy-roo here. Move this vertex and do a little flippy-roo this way. Just do everything I can to try to not make the same triangle again. In fact, I might even take an opportunity to do some maybe reflecting as well. But in the end, again, I have to make a triangle. I have to make the same triangle. I'm trying to make the same triangle, or show that I cannot. And there we have one that's red. So we have an opportunity here to visually inspect these two. But if you look down at the bottom, you immediately see these triangles are probably going to be the same. The side lengths have to stay the same. The angles here are the same. Now visually, again, if we want to inspect this, I'm going to have to perform a little reflection here and a little vertice rotation. But in the end, those triangles are precisely the same triangle. So by fixing the sides, we are in fact fixing the angles. Now, I would argue this is explained in kind of a slightly different way. This might be better explained through the idea of fixing points. So I have this red length here, I have this blue length here, and this black length that I can't change. Well, I know where these 2 points are, the ones attached to the either end of the black segment, because they're the intersection of these 2 side lengths. Like, so the red side length and the black side lengths come together to form this point. The black and the blue come together to form this point. So these 2 points, I'm going to call them point 1 and point 2, are actually fixed. I know where they are. I know the location. I can't change them. Now, of course, I can transform them, but we all know that's not actually changing anything. They're rigid transformations, those transformations so far. But this point right here that I can move seems to be kind of floating out in space. Like, it has many possible different locations. As long as I'm staying the red distance away from the point 1, I should be set to go. Same thing is true for this point right here. I know it has to be the blue distance away from this vertice, but really, as long as I put it blue distance away in any direction, I'm still following that blue direction out. Now, I think side, side, side works less because the sides are fixed, but since I know all those side lengths, this last point is actually fixed. It's not correct to say that these points are floating out in space, but rather there's only a single place where both those distances, red and blue, are going to meet. And because it's only a single distance, that means A was actually set to begin with. So I would argue that side, side, side lets you know the beginning locations of all 3 points. They're not ambiguous. I cannot make more than one triangle, so that when I do transform it to my original image triangle, they have to line up. Again, because you can only make one triangle before the transformation, of course, is going to preserve that. Let me show you what I mean by showing you a counterexample. So let's take side-side angle, for example. The red length is fixed, the black length is fixed, and this angle here is fixed. I can actually move this arrow in and out because I don't know that side length. I just know that I have this side, and this angle, hence side-side angle. So the third point of the triangle is unknown, it's unfixed. These 2 points can't move relative to one another. but I got this red guy who can just kind of all over the place and move. So I still need to make a triangle, so I'm going to try to do my best to do that. And there's one right there. But I think I also have the freedom to make a different triangle. Let me explain what I mean. I think if I move this red distance here, because this arrow distance was variable, look at that, I can make another distance, I can make another distinct triangle here. Now, we can test this, because I know that the AB length has to be the same as the AB length here, and it is. I also know that this red length, this CB length, has to be the same as this CB length. I can test that. And then, of course, the A angle has to be the same as the A angle. And there it is right there. So this potential shortcut isn't actually a shortcut at all. It doesn't work. And I would argue the reason that it doesn't work is simply because I could not fix all three vertices given this information. I could fix, in other words, set in stone A and B. I can't really move those. But C actually had two possible locations, hence it's not fixed. I would say it's fixed if there's only one potential location, but because B can exist, or I'm sorry, C could exist here, or C could exist here and form a triangle, that third point is variable given this information, therefore cannot assume triangle congruency. So once I transport it, if I didn't know what I'm transporting to begin with because there are two possibilities, I cannot guarantee the end result is going to be the same as the beginning result. I just can't because I never knew what the beginning information was. So when we're examining one, say like SAS, that's the kind of the question I have to bring myself to. I know that this point, the one I'm grabbing and moving, and this point at the end are going to be set. In fact, I can't even move that one because these 2 point locations are given to me. This guy right here, though, since I have the freedom to move it around, the question I really need to ask myself is this point right here preset, or can it take on more than one location and still make a triangle? I would argue in this case I only have one location. The reason why is because this angle here between the black line and the red line is set in stone, is fixed, so to speak. In other words, I have to put my red line there. And since I still have to form a triangle, I believe that's the only triangle I can form. If I were to move this A distance, or this A vertice up, I wouldn't even have a triangle anymore. In fact, it's a triangle that I'm trying to make simply because I have to keep that angle the same. So I cannot move it up, and for the same reason I can't move it down. I also can't move this A in or out because the distance is fixed. So because I would argue that SAS works simply because you have a set location for A, B, and C given the side angle side information. Same should be true for angle side angle. For angle side angle. I have location 1, I have location 2. Does that mean location 3 can be more than one space? Well, I would argue no. Because these angles are fixed, even though the sides aren't, they still have to meet to make a triangle. And I would argue this is the only triangle that they could possibly make. I can't move this arrow left or right because that would change the angle. I can't stop it because I wouldn't make a triangle. Now you could argue, well, I could flip it this way because I never said which direction the angle has to travel. True, but that just means I have to flip the guy this way. And hopefully when you look at these two triangles, you realize, well, one is just a reflection of the other. And reflection, since they're rigid, preserve congruency, i.e. they're the same triangle. So that is why, if I look at my list, and I'll blow it back up, that is why side, angle, and side work as a triangle congruency shortcut, because that information will actually fix the points in place. And if the points can't move, and the points are definite, and the points are not variable, that means a triangle, once transported, should be the same as when we started. For that same reasoning, side angle doesn't work. I know where these 2 points are located, but this point right here actually has 2 different OK locations. I can make a triangle here, just because I don't have the right combination of information. But I could also make a triangle here, not violating my distances or the angle I was given, but simply because I have more options of where that third point can be. If there are 2 options of where that third point can be, therefore if there are options, I cannot claim that given side angle, I will always have the same triangle. In fact, I can argue I have two distinct ones I could choose from. Okay? So I hope that helped a little bit. This is a complex idea, guys. We'll be talking more about it. This is kind of our entry point into it. But again, this is giving you some visual evidence and maybe some point analysis about why angle, side, angle, side, angle, side, angle, side, and side work. And side angle simply does not. It has to do with knowing where all the vertice locations are for your triangle. And that's what I got for you guys. Thank you. Thank you for watching. Don't forget to take notes over this section as well. That's posted too. And I'll see you guys later.